Welcome to this video that will now discuss the solution to the iterative activities with the activities going over the iterative parts of the algorithm shown in the Part A lecture notebook of the fourth module. So I'm really just going to show solutions for the improving the secant algorithm activity. I'll discuss how you should go about comparing secant to false position, because that's more of, again, a summary activity that's in line with how we ended the bracketing part of this lecture notebook. And then the last thing is the summary activity, which you have to do yourself. But let's just look at what I'm asking you to do for improving the secant algorithm. The same notes as the first two activities apply here in terms of you might need to create like a lot of code in markdown cells in addition to what I have to do what you want to do, but I'm just going to go ahead and jump right into it. I want you to create a mySecant function that is improved from what is implemented in the secant method for demo in the sense in which it is improved is that it checks for and avoids any potential errors. For example, don't divide by zero. That may occur both before any computation takes place and also during runtime. So let's go ahead and look at the secant method for demo. So this is this code. Let's go ahead and copy it and put it down here. Now, the first thing, create a mySecant function that is improved from what is implemented here. So, well, if it's supposed to be called mySecant, you better change the name, mySecant. And then we want to check for and avoid any potential errors. So we never want to divide by zero. So what should we do? We should check here, right? We've created this initial list here. I would say you can do this elegantly as follows. Before any computations take place, which is right here at the start of each loop, after we've gone and done our approximations, which here we loop through and improve them, and we start with this initial list, this is the perfect place. You can check right here. Am I going to divide by zero or not? If I am, I should just let the user know, stop, and return the actual list right there. So in this case, I should just say, look, if the f of x1 is equal to f of x0, right? And that's actually not even that. You want to check not if they're equal, but if this is really close to zero, I would do it like this. If the absolute value of f of x1 minus f of x0 is, let's say, smaller than, we can do like you can basically say that. You could either make this equal to zero, which is not going to be equal to zero because it's going to be round off, but you want to make it smaller than, let's say, some tolerance. So let's, in fact, improve this. I would do it this way. There's other ways you can do this, but I'm going to show you kind of a more advanced way to think about it. So let's say the tolerance, this is just a tolerance for division. Let's make that equal to, let's say, 1e to the negative 7. So as soon as f of x1 and f of x0 are within, let's say, 10 to the negative 7th from each other, then that's a good place to say, I'm getting close to dividing by zero, and we just want to stop. So if that's the case, we want to just print, a division or near division by zero is about to occur. And then, so we'll do a new line and say exiting algorithm. And at that point, we should just return the x's and f's that we have at that point. And then else, we just continue on. So we don't need any else condition because we'll just keep doing that, right? Because we're basically breaking out of the function as soon as this happens. You could also, I think, use a break here if you don't want to have two return commands. So this would break out of this for loop. So we could run it like that. Either way. So that's it. There's different ways you could do this. You could just check to see if you're actually, if that difference is equal to zero or approximately equal to zero within some machine epsilon. I've shown how to check things within machine epsilon values that are stored in the computer in different algorithm or different lecture notebooks. So you could go do that. That's about it. This is all I really want you to do in this code. Something like this. And how you do it is up to you, but I think it's best to just, not look to wait till you're within machine epsilon. It's kind of wait till where you're even within an allowable tolerance. And you can change this by having it as a parameter. You allow the user to change what that tolerance is. So now I will create a myPlotSecant based on plotSecant above that utilizes this secant instead of this mySecant instead of the demo one. So this again is the plotSecant. I will just copy and paste. So I copied it. I now paste it here. Oops, let me close that. Control V, there we go. And I'm going to call it my plot secant. In this case, since I have this tolerance parameter, it makes sense to set it or just leave it. I mean, I'm not making it necessarily like very advanced. So we could, to do the minimum required to satisfy these instructions, I have my plot secant, and instead of calling secant for demo, I am calling my secant. That's it. That's all you have to change here. Everything else below is just plotting. So if you do that, you've satisfied this part of the instruction. Now, if you want to have this tolerance as something that you can set in the plotting, then you should take that parameter, put it here, and then pass it into the mySecant. If you have it here and you don't use it, that's wrong. If you have it passed to the function, it should be used for something. So it should be passed into here. And that's like the first, I discussed something like that in the first solution activity video. But I'm just going to use the default, so that's it. I run that. And now test your code on some Lambda functions. So that means at least 2 using the interact widget on your myPlotSecant function on this one. And again, I think at this point, you know how to do this. It's very much like what was shown in the solution activity videos for the first 2 activities in the bracketing method part of this. So I'm not going to do that in the interest of time, because these videos I know are kind of getting a little bit long. But you should be able to do that at that point. If you have questions, please post them on Canvas about how to do that. But I think at this point, you need to be able to do that on your own. And then as far as comparing the secant to false position, they're similar types of algorithms. They both take roots of lines. The difference is that the false position is a bracketing method and the secant is an iterative method. So again, you should read up a little bit on those, understand the differences, and explain these differences here, and show some examples where one does better than the other. And also just the advantages and disadvantages of these approaches. Like secant's a little bit more flexible, but that flexibility comes with a price in that it might not always work. False position requires you to know more information than secant in order to set it up. Like these are some things that you should talk about and show examples of those things in here. And then of course you have your summary. But I'm just going to stop this here so that these videos don't take up too much of your time in watching them and helping you solve the embedded activities in the Part A lecture notebook. Thanks for listening.